Hey guys, welcome back to another video in the series where we talk about fundamentals of mass transfer. Today we'll be looking at a problem that looks at the multi-component steady-state gaseous diffusion in a Stefan tube. So without further ado, let's go right into the problem and see what it's all about. Okay, so what we have here is a Stefan tube, and inside this Stefan tube there's a liquid mixture of acetone and methanol. And the Stefan tube is covered by a screen on top, and there's a very high velocity air blowing right on top of it in this direction. So the main purpose that the air serves is that as soon as the acetone and methanol gas molecules escape from this tube, the air is blowing so fast that it gets removed right away. So what this means is that the molar concentration of acetone and methanol at the very top here is actually equal to 0. And and since we know that the total mole fraction should always be equal to 1, the mole fraction of air in this area should be equal to 1. So likewise, what we've been given is that at the gas-liquid interface right here, the mole fraction of acetone is 0.319 and the mole fraction of methanol is 0.528. And we also know that the pressure inside the Stefan tube is 99.4 kilopascals and the temperature is 328.5 kelvins, and they're both constant inside the Stefan tube. What we've also been given is that the distance from the gas-liquid interface and the screen at the top of the Stefan tube is actually equal to 0.238 meters. And on top of this, what we've also been given are the Stefan-Maxwell diffusion coefficients for the three components, which are given right here, and they're written in the units of millimeters squared per second. One last thing, the main function that this screen serves is that when the air is moving at high velocity right at the top, the screens prevents the air from coming inside and creating turbulence inside the Stefan tube, so that it doesn't disturb the diffusion that's happening inside. One thing to note is that it's not preventing air from coming inside at all, it's just preventing the turbulences from being created. So yeah, with all that information, what we're trying to look at is how the mole fraction of the three components, the acetone, methanol, and air, will vary with the distance. So, okay, since we've been given the three diffusion coefficients, let's just start off by writing down the Stefan-Maxwell relationships for them. So what we know is that the Stefan-Maxwell relationship is given by this particular equation, where the mole fraction gradient is actually equal to the summation of the mole fraction of the first component times the molar flux of the other component minus the mole fraction of the other component times the molar flux of the first component, which is all divided by the total molar concentration times the Stefan-Maxwell diffusion coefficient of the two pairs. So before we expand this expression, let's assume that we are in ideal conditions, and for ideal conditions we know that concentration is equal to pressure divided by the gas constant times the temperature. So once we put down all those values, we get the number 36.39 for the total molar concentration. And this won't be used right away, but it will become useful once we get to the later half of the calculation. So it's better to get it calculated right away. So when we expand the Stefan-Maxwell equation, what we end up with is this relationship for the first component, which is acetone. We realize that the first item in this series is equal to 0 because the numerator is actually the difference between two same and equal values, so that goes to 0. And what I've written here, the third component, is that the mole fraction of component 1 and the times the molar flux of component 3 is actually equal to 0. So why is that? So let's start by looking at this main relationship. So what do we know about this in our problem? So we don't know what the the mole fraction of any of the components are at all points, and we don't know the molar fluxes either. But we do know the concentration, and we do know the Stefan-Maxwell diffusion coefficients. Now, in this problem, these four components are actually constants because the temperature and pressure inside the Stefan tube are constant. The concentration has to be constant, and the diffusion coefficients are obviously constants to begin with, so they won't change. The reason the molar fluxes are constant is because we've already established that the pressure is constant at 99.4 kilopascals. So at all points in this this part of the Stefan tube, we know that the molar fluxes have to be constant. The reason is, if it were not constant, pressure would not be constant. There would be regions of high and low pressure, and that is not what's happening in this problem. So we know that the molar fluxes are constant. We also know that the mole fractions are not constant because it's diffusing. So obviously it's going to have a higher concentration at one point and lower concentration at the other. That is basically how diffusion even occurs. So we can safely say that the y1 cannot be equal to 0 because it's a variable and it is not 0 at all points. So we come to the conclusion that N3 is equal to 0. Now N3 being the molar flux of air, the reason that's 0 is because air cannot mix with the acetone-methanol mixture. So no air molecule is going from the gas to liquid in the gas-liquid interface. So we know that the molar flux has to be constant throughout the length of the Stefan tube, and the molar flux of air at this region is equal to 0. So by that we conclude that it has to be 0 at all points in the Stefan tube. So that's the reason we say N3 is equal to 0. So we finally end up with this relationship, this Stefan relationship for acetone, and by doing the same calculations, we can say that the Stefan-Maxwell relationship for methanol is that. Now, if we look at these two equations, we realize that both of them are initial value problems. We know what the values of y1, y2, and y3 are at z equals to 0. And what we can do is treat both of these equations as simultaneous equations and try to solve them. So one way to approach this is that we make an initial guess for N1 and N2 and then solve this simultaneous equations, and then we try to get the value of y1, y2, and y3 where z is equal to delta, which is at the top of the screen. And then if the values of y1, y2, and y3 are 0, 0, and 1 respectively, we know that our initial guess for N1 is actually correct. But if that doesn't happen, what we can do is we can improve our guess. We make another guess based on our initial guess, and then we keep on iterating until we get those until we get 0, 0, and 1 for y1, y2, and y3 respectively. So after we do that, we get the values of N1 and N2, and using those values we can plot out a graph for the mole fractions of the three components at any point in Z. So now that we know how to solve this problem, let's actually standardize this problem first, because right now we're dealing with this diffusion situation in a Stefan tube where the dimensions are relatively large. But we might have to deal with a situation where we're looking at diffusions within cells, and in that case our numbers can get extremely small. So and that can be pretty tedious to deal with. So what we can do is scale our z with respect to the maximum value of z, so that we can assign a new variable for distance, which can only range from 0 to 1. So how we do that is that we assign this variable eta, which is equal to z divided by the maximum distance, delta. And what we get from there is that we will have to change all of these z's into etas as well in order to being able to solve these differential equations. So what we do is we take the dy over dz and use chain rule to convert it into that equation. And what we do from there is we substitute the eta with z over delta. And if we take the derivative of that, what we get is that. So dy over dz is equal to dy over d eta times 1 over delta. So if we substitute that relationship into our Stefan-Maxwell relationships, what we end up with is this relationship for y1 and that relationship for y2. So we finally have our Stefan-Maxwell relationships, which have been standardized to fit all kinds of problems. So now, a problem that we've run into here is that solving this differential equation can be very tedious because we're making a guess, and we're making a mistake, and we're making another guess based off of that, and then we keep iterating until we hit our solution. But that can take a very long time to be done by hand. So what we can do is actually solve this problem on a computer by using Python. So we could do that, but another problem that we run into here is that what do we guess for n1 and n2? What is a good guess? Can we go with 1? Can we go with 10 to the 5? Can we go with 1 septillion? So we really don't know what a good guess is. And the problem is, the more inaccurate our guess, the longer it's going to take for the computer to solve. And once we start getting into really big numbers, what could happen is that the computer either just won't be able to solve, or it'll just give us an inaccurate solution, which might be completely wrong. And the latter is very dangerous because we might be out there seeing like we solved a problem and got the correct solutions, when in reality it's not the right answer, and that could lead to a lot of problems. So here it becomes really important that we make a good guess to feed to the computer. So how do we do that? And a way to approach this is through scaling. So what that means is that we only take into account the order of magnitude of all the variables that we have in our equations, and using that we try to estimate what the order of magnitude of our guess should be. So how do we do this? Let's take a look. So first of all, I'm starting by simply saying that our Stefan-Maxwell equation is simply equivalent to that, because the other terms are essentially going to be the same order of magnitude as well. And so yeah, that's why we reduce the Stefan-Maxwell equation to this. And first of all, we're going to say that the dy over d eta is going to be equal to 1. I'm going to explain later why that is a good assumption, but let's say 1 is a good assumption for now. Likewise, we know that the mole fractions only range from 0 to 1, so I say that y1 is equal to 1. And then our molar fluxes is what we're trying to get, so I'm just going to go with x. Same thing here. And then we already know that our concentration is equal to 36.39, so that's the first order of magnitude, which is 10. And we know that the Stefan-Maxwell diffusion coefficients for gases is in the order of magnitude of -5. So that's why we say d12 is equal to 10 to the -5. And then delta, again, ranges from 0 to 1. So we just go with 1. And so what we're trying to get at here is that what should the order of magnitude of these x's be so that this side of the equation becomes equal to 1. And the answer is 10 to the 4. If the numerator is equal to, we know that the denominator is equal to 10 to the 4. So in order to be equal to 1, the numerator also has to be equal to 10 to the 4. So that's why x we assume to be 10 to the 4. So this is why we guess that N1 and N2 are both equal to 10 to the 4 moles per meter squared per second. Now, so why was the guess that dy over d eta equal to 1 is a good assumption? Let's take a look. So according to my assumption, the graph of y and eta should look like this. But does it actually look like this? And the answer is probably not. It probably most likely looks something like this, which is close to being the gradient being equal to 1, but it's not exactly 1. It might be somewhere like 0.1, 0.2, 0.3, something like that. However, could there be a case where the graph actually looks like this, and the actual value of dy over d eta is equal to something like 10 to the negative 5, 10 to the negative 10? Could it be? And that's certainly possible, but it's extremely unlikely. And the reason why is that whenever something like this happens, the most likely reason is that when we scaled eta with z and delta, that was probably done in a bad way. So when we said that delta is actually at the top of the screen, that was a good thing to do. Now, what leads us to situations like this is that when we say, for example, delta is actually at the top of the room, at the ceiling of the room that we're conducting this experiment in. So what that means is that our the mole fractions go like this with respect to z, not eta. And then when it reaches the top of the screen, it's just going to go, bam, drop to 0. And then all the way up to the ceiling, it's just going to be a straight line of 0 all the way to the top. And when we make a graph of eta by starting off with this data, it's going to end up being this graph that we have right here. So this is a case we end up with when we take our maximum value to be way unnecessarily large. So, and that's not something we've done here. We've made a pretty good maximum value, which is at the top of the screen where the diffusion matters the most from the gas-liquid interface to the screen. So that's why we can say that this is actually a good assumption to say that dy over d eta is equal to 1. Now that we have that out of the way and we have set up our problem so we can solve this in Python, let's get right into coding this out. So yeah, I'll see you guys in a bit. So before we go ahead and immediately start coding this problem out, what I'm going to do is give a brief overview of the flowchart for the problem that we're trying to solve and get a better understanding of what we're trying to do, so we don't get too confused in the middle of coding. So what we're going to do is, first of all, we're going to import our libraries, and then we're going to input our parameters, all the numbers that have been given to us by our problem. And after that, we're going to calculate some things that are fairly straightforward to calculate. And after that, we're going to set up our Stefan-Maxwell differential equations. It's not exactly straightforward to do in Python, so we're going to have to create a function of the two differential equations so Python can actually do calculations on it. After that, we're going to make an initial guess for our molar fluxes, and once we're done with that, we're going to try to solve the initial value problem to get the mole fractions at all eta. In order to do this, we're going to be using the solve IVP function from the SciPy library. And after that is done, we're going to set up an iterator to calculate y1 and y2 at eta equals 1 for any value of n1 and n2. And once we have that, we're going to try to calculate the value of y1 and y2 at a given value of n1 and n2. And we're going to see if y1 and y2 is actually 0 when eta equals 1. So if the answer is yes, we're simply going to solve the IVP again, but this time we're going to use the actual n1 and n2, and from that we're going to try to get the values for y1 and y2. But if our y1 and y2 are not 0 at eta equals 1, we're going to make a new guess for our n1 and n2, and then we're going to keep doing this process until we actually get a point where a given value of n1 and n2 gives us y1 and y2 equals 0 at eta equals 1. This sounds a little bit complicated to do, but it's not going to be that difficult because Python has a function that enables us to do that, which is a root function from the SciPy library. So that's what we're going to be using. And once we have the values of y1 and once we have the actual value of n1 and all the values of y1 and y2 at eta, we're going to create an array of the values for n of eta, and we're also going to calculate the corresponding values of y1 and y2 for all eta. And once we have all of that, we're just going to plot a graph and see how the mole fractions of acetone, methanol, and air vary with the distance. So, okay, let's start coding this out. As you can already see, I have already imported everything that we need to. So first of all, we imported the numpy as np. This is going to be useful when we're creating arrays. And from the scipy.integrate library, we imported the solve_IVP. This is going to allow us to solve the Stefan-Maxwell relationships. And then again, from the scipy.optimize library, we imported the root function, and what this is going to allow us to do is it's going to help us obtain the actual value of n1. We're going to see a little bit later how that's going to happen. After that, we imported the make_subplots function from the plotly.subplots library. This is only so that we can actually plot the graph. Plotly.graph_objects also will help us plot out different graphs. In this case, we're going to be using a scatter plot, and this library is actually going to allow us to plot a scatter plot. After that, we imported plotly.io as PIO, and the reason we did that is in order to be able to change the appearance of the graph. The line immediately after that, this line, what it enables us to do is it helps us change the theme of the graph, and we're going to make it a dark theme because it matches well with the rest of the aesthetics of the whole Google Colab. Yeah, so once everything's been imported, we put down all the input parameters. We have pressure at 99.4 times 10 to the power 3 pascals. We have the gas constant, then the temperature, and we know that our delta is going to be 0.24. It's actually 0.38, so let's make it that. And then we have our initial values for y1 and y2. That's 0.319 and 0.528. These are the mole fractions of acetone and methanol at the liquid-gas interface. We have also been given the diffusion coefficients, which are as follows for the three pairs. And okay, so let's do the simple calculations first. We can easily calculate the molar concentration of the mixture. So let's go ahead and do that. P over R times T. So that's the molar concentration of the gas phase. And then what we're going to do is assign a variable called F12, and this is simply going to be equal to concentration times D12 divided by delta. And where this actually comes from is it's right here. This concentration times D12 divided by delta. The only reason we're doing that is because it's going to be a lot easier to type F12 than typing out this entire thing multiple times throughout the code. So yeah, we're going to do the same thing for F13, and that is going to be equal to concentration times D13, the diffusion coefficient of the 1,3 pair divided by delta, and the same thing with F23. That's going to be equal to, oh, my bad. Let's copy that and paste it here. It's going to be 2, 3. Yeah, so that's all the things we need to be calculated right now. So let's take a look at our flowchart again. We have our libraries, we have our input parameters. Now what we need to do is set up our Stefan-Maxwell equations. But before we go ahead and do that, what we should first do is take a look at how the solve IVP function actually works, because ultimately that's what we're going to be using to solve our differential equation. So it would be helpful to know how solve IVP would like us to set up the differential equation so we can use it later on. So let's go ahead and take a look at the solve IVP from SciPy. All right. So what we can see here is our differential equation is there, and that's how solve IVP wants us to set up our differential equation. So our differential equation should be a function in which the first parameter is the independent variable and the second parameter is the dependent variable. So how this relates to our problem is we're calculating dy1 over dz. So our function, my bad. So what we're calculating here is dy1 over d eta. So our function should therefore be a function which takes eta first and then y1. So let's go ahead and make that function. So what we can do is define our function. Let's call it dy. The first variable that it takes should be eta, and the second one should be y1. But instead of doing that, I'll just make the second variable y so that we can set up both of our differential equations for both y1 and y2 in the same function. So let's go ahead and do that. And I'll say that y1 is equal to y0. So what this means is that our y here should be an array, and it should be an array with two values, y2 equals y1. Yeah, so y should be an array with two values in which the first element should be equal to y1 and the second element should be equal to y2. So yeah, that's our inputs, and we know that y3 is simply equal to 1 minus y2 minus y1. So this is because the total mole fraction should always be equal to 1. And what we want this function to return is the actual equation. So np.array, we're creating an array here, and this array is going to have two elements. The first one will be the Stefan-Maxwell relationship for acetone, and the second one will be the Stefan-Maxwell relationship for methanol. And those are these two equations, this equation and that equation. So the one on top will be the first element in the array, and the second one will be the second element in the array. So let's go ahead and type that out. So that's going to be y1 times n2 minus y2 times n1, and all of this is divided by f12. Remember that c times d12 divided by delta is simply equals to f12, and subtract that from y3 times n1 divided by f13. And then our second element is also going to be very similar to this. So I'll just copy and paste it. except that y1 is going to be y2, that's going to be n1, that's y1 and n2. And there we have it. Those are our two Stefan-Maxwell relations. Now, what we eventually want to do with this is that we want to solve this differential equation. And in order to do that, we're simply going to use the solve IVP function. And let's see. So let's see how this is supposed to be set up. So so it's just telling us that the first argument should be the function, and then the t-span, which is simply the it's simply the span over which we're supposed to integrate. So in our case, it's supposed to be 0 to 1, which is the values for eta. And y0, this is simply our initial starting values, and that's going to be the initial value of y1 and y2. And then the method we need to specify, for this case, we'll be using Rado method. It's not important to get too deep into it, so we're just simply going to use Rado. And then what's important is that we need to set the dense output functions to true. So what that's going to do is that it's going to give us an output which is continuous. And we want those values because we want multiple values from 0 to 1 for all of the mole fractions. So let's go ahead and try to solve it. So our function is simply going to be dy. Our t-span is going to be from 0 to 1, all the values of eta. And then our starting conditions is simply y1 initial, comma y2 initial. They have been specified right here. And then we set our method to Rado, and our dense output should be put on true. So let's go ahead and run that. Okay, so we ran into an error here, and that's because the name n2 is not defined. Okay, so let's go ahead and define n1 and n2 first. So on top of this, n1 is going to be equal to our initial value of n1. Okay. Right here, I'm just gonna put down our initial guesses for n1 and n2. We've already established that our initial guess is going to be 10 to the negative 4, so 1e negative 4, and n2i is also going to be equal to 1e negative 4. Let's go ahead and run that, and we'll set n1 as equal to n1i, and n2 as equal to n2i. So let's go ahead and run that, and there we have it. So it actually gave us a solution, but this isn't exactly what we're looking for. So our solution, according to this message, is right here. So what this is actually giving us is that it's giving us a solution that can be accessed for certain values of eta. So if we want to solve this IVP for an eta of, say, 0, we're going to have to write down a line of code. So let's go ahead and do it. What we're going to have to do is I'm going to store this solution in a new variable. So let's call it res underscore IVP for result of IVP. So we store that under there. And then in order to access the solution for certain values of eta, what we do is res underscore IVP dot solve because it's inside solution, and the value for which we want the values for y1 and y2, let's say it's 0. So let's go ahead and run all of that. Okay, and there we have it. So it just returned us the initial values of y1 and y2. So in the same way, we can run this solve this IVP at eta equals 0.3, and it gives us those values. And ultimately, we're going to need the solution at eta equals 1. That's going to be 0.3 and 0.5. This is obviously not correct. We're supposed to get to 0 and 0. But we're not getting that here because this IVP solver is basically working off of our initial guess of N1 and N2, the molar fluxes. So what we need to do from here is actually find what the correct value of n1 and n2 are. So let's get back to our flowchart and see where we're at. So we just set up the Stefan-Maxwell equations as functions. We gave them our initial guess for the molar fluxes, and then we solved the IVP to get the mole fractions at all eta. And then what we did was we specifically looked at what the values of the mole fractions would be at eta equals 1 from our initial guess of n1 and n2. So now what we need to do is set up an iterator to calculate y1 and y2 at n equals 1 for any n1 and n2. So what that means is we need to set this problem up so that we can continuously change the values of n1 and n2, and based off of that we should be able to iterate and get multiple values of y1 and y2 based off of those initial values of n1 and n2. So let's go ahead and treat this whole entire thing as a function, and we're going to see in a bit why that's important. So we go ahead and do that, and then we define it as a function where the function takes input n. And then what we can do here is n1 could simply be the first element in the array of n, and n2 can be the second element in the array of n. So what this means is that this is a function that takes the two values n1 and n2 as an array, and it returns us the solution at 1. So in order to do that, what we can do here is so return that. So okay, that works. So what this part of the code basically does is that it takes two values, n1 and n2, and then it gives us the values of y1 and y2 when eta equals 1. Okay, it looks like I've made a small error here. So when we calculate the value of concentration, I did not include R and T in parentheses because we know that it's actually P divided by the product of R and T, not P divided R multiplied by T. So by not putting in the parentheses, how this worked was that Python calculated P divided by R first and then multiplied the result by T. And let's actually see the results right now. Yeah, so when Python did that, what the value of C came up to be was this very large value. And we've already calculated this value, and we know that it's not exactly true. So let's put the parentheses in and see what the value of C is. And there we go. That's our actual value of 36.39. So yeah, this is a good time to remind ourselves to be very careful with parentheses when working with numerical calculations in Python. So yeah, so let's go ahead and run all of the program again with the correct value of concentration. And yeah, so what we get is this value. So what that is basically after solving all of this, what we found out was when n1 equals this value and n2 equals that value, the values for the mole concentration, mole fraction of acetone and methanol both become very close to 0. So yeah, so with that knowledge in mind, what we can do now is solve the IVP again in the right here. So what we can do now is we can solve the IVP one more time, but this time we use the actual value of the molar fluxes of acetone and methanol, and we use that in order to calculate the mole fractions of the two components at all values of eta. So yeah, let's go ahead and do that. So the molar flux of acetone is simply going to be equal to yeah. So one thing we need to do here again is that we need to access these two values from that function. So in order to do that, we're gonna assign a variable to the function. Let's call it res underscore n for result of n. and our n1 will be equal to res underscore n dot x, and since it's an array and we're trying to access the first value of the array, it's going to be x square bracket 0. And same thing for n2, the molar flux of methanol, it's going to be res underscore n dot x square brackets 1. So that's accessing the second value from inside the res underscore n variable. So let's go ahead and run all of that. And let's see what the values of n1 and n2 are. Okay, I made a small error there. Alright, let's see. Okay, it looks like I didn't capitalize the n. Alright, there we go. So that's our value for n1, and our value for n2 is there. Now that we have our actual values of n1 and n2 assigned to these variables, what we'll do is solve this IVP one more time, but this time with the actual values of n1 and n2. So we have already written down our IVP solver, so what we're going to do is simply copy and paste that part. Let's copy that and paste it here. We don't need this part. And all of this should be, their indentation need to be fixed. Shift tab, and there we go. So what this part basically does is solves the IVP with the actual values of n1 and n2. So yeah, we're done with that part. Now looking at the flow chart, we have solved the IVP to get all y1 and y2 for n1 and n2 at all eta. Now what we need to do is create an array of values for eta. So let's go ahead and do that. I'm going to call the variable for eta to be eta underscore array. And what I can do here is np.linspace 0, 1, 51. So what this basically does, it creates an array starting from 0, ending at 1, and it includes 51 equally spaced values in between. So what that looks like is that. So those are our values for eta. Remember that eta is our independent variable, so we can just assign any values to eta between 0 and 1. So now that that's out of the way, now let's make an array. The other part is create an array of corresponding values of y1 and y2 for eta. So in order to get the actual value of y1 and y2, we're going to have to access this part. And so first of all, I'm going to call the variable y underscore array, and what we're going to do is actually try to access those values from here. So just like we did last time, res underscore IVP dot sol, and this time instead of having something like 0 or a 1, what we're going to do is simply put in the eta underscore array inside. So let's see what it actually gives us. Okay, we get this huge two-dimensional array, and what this basically means is the first array is the corresponding values of y1, and the second array is the corresponding values of y2. So to be more exact, okay, it looks like I can only get one at a time. So let's do that, and eta underscore array. Okay, so when eta is equal to 0, our value should be, for y1 should be this, and y2 should be that. And likewise, when eta equals 0.02, y1 should be that, and y2 should be that. And it keeps going on. So all that's left to do now, since we have all the values we need, we just need to plot this out. So what we're going to do is create a figure, fig equals make underscore subplots, where rows equals 1 and columns equals 1. What this basically does is it creates a graph of a 1 by 1 graph. It means that if we do something like a 2, 1, it's 2 rows and 1 column. There's gonna be 2 graphs, one on top of the other. And if we do like a 2, 2, there's just gonna be 4 graphs, 1, 2, 3, 4, just like that. So since we need only one graph, we're just gonna go with 1 row and 1 column. Now we need to provide all the things that we're gonna plot. So what we're gonna do is fig.add_traces brackets go.scatter, so that we can actually do a scatter plot, brackets, and our x is going to be equal to eta_array, and our y is going to be equal to y_array. I want to first plot the graph for acetone, so I'm going to access the first element from inside the y_array array, and we're gonna call it name equals acetone. So let's go ahead and see what that looks like. So yep, that's our graph for acetone. Its mole fraction is decreasing as we go higher up in the Stefan tube. And now let's add the methanol. So we're just going to copy and paste that, change that to the first element from inside the y_array, and the name should be methanol. Let's go ahead and see what that looks like. There we go, the red one's for methanol. And finally for air. We know that the mole fraction of air should simply be equal to 1 minus the sum of the mole fractions of acetone and methanol, so we're just simply going to do that calculations right here. y_array 1, and then the name should be air. And there we go, that's our final plot. We can see that the mole fractions of methanol and acetone are decreasing all the way to 0 when it gets to the top of the Stefan tube, and meanwhile the mole fractions of air is decreasing all the way up to 1. So yeah, we've reached the end of our problem. I hope you guys learned something today, and I'll catch you on the next one. Bye bye.